Hi everyone, this is Professor Granucci, and what I'm going to do in this video is talk about, oops, I missed it. There we go, impulse and momentum. So I'm actually going to do a lot of similar things we did in Newton's laws, particularly Newton's third law, where it says when any two objects interact with each other, they feel the same force, and Newton's first law with the law of inertia. Essentially what I'm going to talk about is the concept of momentum as being moving inertia, talk about what it means to generate this thing called an impulse, and then actually, although this is the big idea I have right here, this will be the second lesson, which is conservation of momentum. But it turns out when things collide with each other, as long as there's no outside forces, the collisions will maintain their momentum. And that is actually more second video than it is first video. So more specifically, what I'm going to go over today is talk about what momentum is in the physics sense, how much momentum, a little fun problem is how much momentum do you need to stop a running back. So usually I teach this during Super Bowl, but you know, that's not what happened, but that's okay. I'll give you an example of calculating momentum. The other thing I want to do is calculate and talk about changing an object's momentum, and then, which is related, talk about impulse. And we're going to talk about the impulse momentum theorem and lots of different applications of this. Like, for example, you know, why do we use padding to reduce the force? You know, for example, like airbags, right? You know, have you ever heard of the term rolling with the punches? I'll talk about why you do that. And of course, some, you know, obvious good applications of physics, you know, winning an egg toss at your next, you know, family picnic or whatever like that. So, I'll definitely talk about those applications as we go through. And there we go. Yeah, impulse momentum. So let's get right to it. So momentum in a physics sense is described as, I'm just going to put this right here. For now, I don't need it just yet. Momentum is described as moving inertia. So kind of the conceptual way of thinking about this is to kind of describe it as, you know, how hard would it be to stop an object if it's already moving? Or I think I have another one, yeah. It's also like a quantity, like a physical quantity of the abilities for that motion to stay, the ability to maintain that object's motion. So just to give you some quick snapshot examples, something that might have a lot of momentum, if you might think about it, even without looking at the equation, might be like a train, for example. A train's pretty big and goes pretty fast. So if I were to try to be Superman and stand in front of it when I'm not Superman, we all can guess the reaction of that. I wouldn't be able to change that object's motion. Could you? Of course, you would need something as fast or as strong to do such a thing. But for example, I'm just not fast and strong enough to do that. So when we quantify an object's momentum, we take into account the mass of the object and its velocity. So that's what you have here, mass and velocity. As always in physics, our masses must be in kilograms and our velocities must be in meters per second. So I was, you know, looking at problems and, you know, a lot of them are actually in grams. So just be aware of the units when you're doing this, that they're in kilograms, not grams. And then if you multiply these two together, the units for momentum is kilograms meters per second, where P is momentum, because M is already mass, so we can't use M again if you think about it. Another important rule is that momentum is a vector, so the signs matter. So if we're quantifying the motion of an object's velocity, we do have to pay attention to which way it's going. Is it going forward or backwards? And of course, as always, if it's going opposite the way we think it's, opposite the forward motion, we're going to throw a negative sign in to talk about the backward motion. And more on this later when we do talk more about collisions. I always talk about football because football is kind of a good example of momentum. If you ever, specifically because most of the time those football players are colliding with one another, right? And you don't need physics to know that the bigger person moving pretty fast will obviously trample over the smaller person moving in any direction, depending on how much momentum they have. So you do see a lot of this in football because that's where you're colliding a lot. Another example of momentum applications is playing pool or billiards, however you call it. That's all about collisions. So that whole game is dedicated to actually having the correct vector, so not only the right speed, but the right direction of that cue ball to hit other balls, so that they can go in the hole. So I always like playing pool because I'm always thinking, the vector addition to how to, sink one of those balls. I'm not really good, but I still enjoy playing it. So we do have to keep track of negative signs. So I do this as a fun example, and you can see how old this is. This was Super Bowl, I don't know, whenever that was, when the Seahawks played. So let's do a quick little fun example here. So let's pretend, for funsies, that I am going to challenge a Super Bowl quarterback. So let's do me. Ta-da. And yes, I will wear a football helmet because that's important. There we go. My football helmet will be purple. Why not? So let's say I have a mass of 50 kilograms. I just picked an easy number. I'm not actually 50 kilograms. And let's say I'm let's ask this question. How fast would I need to go to kind of challenge Tom Brady, right? So let's go ahead and let's figure out Tom Brady. There's a Wikipedia, of course, on everybody, right? So let's go ahead and find Tom Brady. I don't know anything about football, so I just picked that because I know that as a quarterback. So we have his mass. Look at that, 102 kilograms. So let's go ahead and come back to this. Let's say that Tom Brady is in a full run. Actually, let's see. He's a pretty tall guy. And he's sideways because he's running. So put a foot there. Put a foot. Oh, no, let's just start over, man. Running, huh? Foot here. Foot here. Here. Good enough. Tom Brady, he's facing this way because he's attacking me. He's angry about it. He's got angry eyebrows. There we go. With his football helmet thing. There he goes. That's how football helmets work. There he is. There's Tom Brady. He's got a mass of 102 kilograms. And let's say he's moving pretty fast toward me. Let's say he's moving a speed of, let's see, well, the fastest human can go 25 miles per hour, so let's not make him super fast. Let's give him like 9 meters per second. That's like 18 miles per hour. See, it's a full run, so it's pretty fast there. So if I want to calculate Tom Brady's momentum, the good news, it's a pretty straightforward calculation. I take the mass and multiply it by its speed. So I'm going to go ahead and do that. So the momentum of Tom Brady is 918 kilograms meters per second. That is his momentum. Now, like I said, this is a vector, so I would need to move at a certain speed to kind of counteract that. So, in other words, I have to have a momentum of 918 kilograms meters per second. My mass is 50 kilograms. How fast do I have to go to kind of cancel this? Like, in other words, not even just push him away, but be able to stop him. So what is my speed? Well, we would set this up just like we did. So momentum is mv, 918 kilograms meters per second is equal to 50 kilograms times v. If I solve for v, I would have to go 18.36 meters per second just to stop this running back. Now, just for funsies, I would have to go 41 2 miles per hour. Basically, I'd have to go as fast as like a car just to stop him. That's actually incredible if you think about it. It's really fast. So even the fastest person in the world wouldn't be able to stop him with this mass, that is. Now, of course, I can change my mass, and then I have an easier time to do that. And you notice that this is, in fact, just about twice as much, because he is just about twice as much as me. Fun fact. Or it would be twice as much as me if I was 50, but like I said, let's pretend that that was my value. But anyway, that's how you can calculate momentum, and if you know the momentum of one object, this is how you find the speed or object's mass to counteract that momentum. Alright, so now we'll go back to here. Okay. Alright, how do you change an object's momentum? So remember that when an object does have momentum, it's going to be, of course, moving with some velocity v. So if you have an object moving at some velocity, it has momentum. How do we change an object's momentum? Stop it with a force, or apply a force. So here's a quick example. Here's an object that has a momentum. It hits a wall, and of course it moves backward. Now notice that the speed is different. So there is definitely some energy loss when you come into contact with things. Also notice that this is a negative sign because it's going opposite the way it came. Very important note here. So again, this is redundant because we talked about this. In order to change an object's motion, you need a force. And that's exactly what we're talking about, just in a slightly different context. In fact, momentum's way more powerful than inertia because now not only are you considering the mass of the object, but now you're considering the velocity as well, which is super powerful. So the amount of force and the time the force remains in contact with the object does affect the change of momentum. So I'm going to talk about that in greater detail with this concept called impulse, which I'll get to in a slide or two. So we can calculate an object's momentum. It's actually pretty straightforward, but I'd walk you through it anyway. So here's our example, right? So the change in momentum is equal to mass times the velocity final minus the velocity initial. Notice that this is the same as writing delta V because delta means change, right? Final minus initial. So in this case here, I have delta P is going to be equal to the mass of the object, which is this right here, 0.25 kilograms. Now this is where people make mistakes all the time, including myself, just because I always want to do initial minus final. It's the opposite. So I need this with the negative sign, 1.1 meters per second minus this number. That's the final. I'm sorry, that's the initial, and this is the final. So that looks like this. Negative 1.1 minus 1.3. I'm just going to do this in steps. Comes 2.4 when I solve for that. Times 0.25. Negative 0.6 kilograms meters per second was changed. Now, if you notice, it's a pretty small number because if you look at the situation, as you can see here, that the velocities before and after, although one has a negative, didn't change too much here. So this is a small change of momentum, which I kind of expected with that. But that's how you can calculate the change of momentum. Leave this here. The negative just means that the change of momentum, or the force, if you think about, occurred in the opposite direction of the motion. And hopefully that makes sense, because if the force, the wall pushes this way, and the object's original direction was actually going that way. Okay. So normally in class I'd have you, you calculate these changes in momenta. Oops. So if you want to pause the video to do that, I recommend that you do it. I know it's so hard to do it when you're at home and no one's forcing you to do it. But it does really help with your understanding if you could take the time to do that. It also breaks up the video because otherwise you're just listening to me talk. So why don't you take a second, pause the video, and calculate the change of momentum for this case. And I'll give you a moment. Okay, so I assume you paused the video and got the following answers. I am going to do these incredibly quickly, assuming that you do understand this. So the final is 0. This is 20. Because it's -3. And then this one. So -5 minus 20. My pen is dying. No good. Okay, so hopefully you got those values. One important thing I want you to notice is the difference between stopping and changing direction. And notice that there is more change of momentum than it is than coming to a dead stop. And actually, this is actually related to force too, which I'll show you with impulse. The force to stop an object is way less than to change direction. So one major application of this is, well, I'll start with bumper cars. If you take your bumper car, which is like this little turtle thing, and you go into somebody, say you're stationary like this, well, case A would be this. Here's your bumper car, you go into somebody, and then you stay together. The force here would be some value. But if you did it and you bounced off, the force is way greater because not only do you have to stop the object, but you have to change its direction. So we always say that bouncy cases have or experience more force. Now, the force between them is the same in both cases, but this one will just have a way bigger force because it bounced off versus this one. So there's a difference between contact between one another in two different scenarios. So what we can say is that impulse generates a change of momentum. So in other words, we can think about it not in terms of how the velocity is changing, but how much force is applied and for how long. This is called impulse. Now, a quick notation. I like to use I for impulse. Online on the homework, they use capital J. This is just a notation. So just note that you'll see this difference with the online homework. Again, I like to use I instead of J. It's just a personal preference. And in fact, if you want to go use J, it's totally fine. But I'll continue to use I. So think about this. The stick exerts an impulse. So not only does it push it, but it pushes it for a certain amount of time. And then, as you might imagine, if it's moving slow, it's now going to move fast after you hit this. This is what we call an impulse. Graphs, because we love graphs in physics. So we can actually look at a real-life case, and what happens is the force actually doesn't stay the same. If I'm gonna kick a soccer ball, fun fact, I was playing soccer today with my daughter, and you come into contact, you'll see that it's not a lot of force. Until you about midway, you get a big compression. This is, of course, a slow motion camera, and then a release like that. So if we look at a force versus time graph, the area equals impulse. In other words, force times time. Now, if I were to find the area of something like this, I'd make it into a triangle, right? it's not a perfect triangle, where this is the height, right? And this is the base. So the area of this would be 1/2 base times height. And that will be equal to the impulse. So if I were to look at that, I'm going to do more examples, but I'm going to go ahead and just do it here. So the height of this is 800, if you notice. So the area of a triangle, of the shape that it made, be 800. And it starts about 30 here and ends about 70. And I think this is in milliseconds, yeah. So the difference between 70 and 30 is 40 milliseconds, so 0.004. Sorry, I know that's hard to see. So 1/2 times 800 times 0.004 seconds. The impulse of this will be 1.6 Newton seconds, because newtons and seconds are here. The impulse is the following calculation. And I do it again. Generally, the shape of these things are like this. I've done real labs where I've done the impulse of a lab, and if I were able to do this live in a classroom, I could actually show you that this in fact is true by colliding something with a force sensor. But notice that it's the same process. Since this makes a triangle, here, it's the height and the base. Good night, Sophia. It's the height and the base, and we take the area of a triangle. And there we go. And then if you notice, I'm just rewriting this, but the 1/2 base times height comes from the shape. It's not always that case. I just want to make a quick little note on this. You could have a case where your graph looks like this. In fact, I hope that the graph looks like this because it's easier. In other words, if it's a square, then it's just those two numbers. If this number is 5 here, and this number is 1 second, then the area of a square is length times width, which is the length, which is, or doesn't matter which one you call which. The length is 5 newtons times the width. So once again, you're finding the area. If it's a curve, then make it into a shape that's easy to solve. That's fine when you do it like that. Okay, so here's another example that you can try on your own. Take a second and see if you can solve for it. I'll take a second and pause. Okay, I hope you gave this a shot. So with the same kind of idea, you want to take because it's a triangle, so I'm going to use the area of a triangle 1/2 base times height. So I need to do 1/2 times the base. So the base is, if you notice, t times hold on. Give me a quick second here. I don't know why I'm having trouble with this. I think this is 1/2 the base times the height. Yeah, so this is the base, this is the height, so it's 1/2 ft, like that. Sorry about that. My fault. Had a quick little moment there. So anyway, I hope you did okay with this question. So now what we can do is do what is called the impulse momentum theorem. So the impulse momentum theorem is the following. In order to make an object change its motion, you need a force. So this equation helps you relate the change of velocity and the force of an object when they come together. This has a multitude of applications. One of them is this one. Again, these are all things that you might encounter every day. Well, maybe not every day. You take an egg and you drop it. But you know what happens. If I take an egg and I drop it on the floor, we know that it's going to kind of crack and splatter and go everywhere. But if I take an egg and drop it on a pillow, it's more likely to, survive the impact of this. So the interesting thing about it is actually the change of momentum would be the same. If I held the eggs at the same height, it would have the same velocity right before it hits the ground. So this whole side of the equation is actually the same for the two of them. So what's the difference? Contact time, right? When the egg hits the ground, it's in contact with the force for literally milliseconds, a split second. And then, of course, the egg feels a huge force. But if the contact time is increased, if the pillow cradles that egg, right, then it will be less likely that it will break because it'll have less force because there's more contact time. So that's the whole reason why at your family picnics, right, you want to take that egg. Not that you would do this and hold the egg up like that and say, I got it. Some people do. You want to take the egg and you cradle it, increase that contact time. Especially when you go really far away and you're trying to like catch that egg that's like, 20 feet away. Trying to cradle it, right? Little sound effects here. So this one is another one with you hear the roll with the punches. So so in a unlikely scenario that you're in a fist fight, if you know it's coming, it's better to go with the punch. So taking that, if I could do this right in the camera, go with the punch and you'll feel less force than doing that. And again, that's kind of common sense, but this is the physics behind it. So one time I'll tell you a little story because, I always like to tell stories in class, but when I used to do karate in college, it was one of my activities I used to do. I got to a brown belt before I left college, and I just haven't been. But you spar a lot, so you're able to, quote, fight other people. Now, with karate that I studied, karate, that you don't actually want to hit people because it shows control, but people get hit all the time. So I was in a tournament once, and I was fighting this guy, and he was a very large man. Like, you know how small I am. So if you, look, this guy was, 6 feet, 3, and, probably 300 pounds, maybe, but, not it was a built 300 pounds. This person was solid. And I was like, great, I gotta fight this guy. And I was doing my best. And, for a little small person, I had my my smallness to my advantage. So it was less likely the person was gonna hit me. However, there was this one part. See, this is where I wish I had a classroom. Can't do it here. The one part where I had to block. So one way you can block is go like that. I'm just trying to see if I could see it. It's not coming out. So you hold your arm like this and you block down. And I saw it from a mile away that I was not going to block this kick. This kick was just going to come right at me. And it did. It came right in my stomach. I saw it coming though. And instead of going into the kick, of course, I went backward. And that's just your instincts. Your instincts are pretty good. I got kicked dead in the stomach and it hurt so bad. And you're not supposed to get hit. So actually, what I did was I took the blow. I basically couldn't see for the rest of the sparring fight. And I sat down and I just started crying. It hurt so bad. But my sensei came up to me and he's like, did he hit you? And I was like, yeah. And he's like, man, you should have just crumbled to the floor. You would have gotten disqualified. And I was like, oh, and here I am trying to be this tough person, even though I cried about it. And I was like, darn. So I'll never forget that. And I will never forget that story, especially when I talk about momentum, because that's ruling with the punches, right? There's your typical family picnic playing egg toss right here. So like I said, you want to cradle that egg when you do that. So I'm going to use the impulse momentum theorem to actually prove another point, which is contact time. So again, we know this already. We know that airbags provide us cushion for when we have any sort of impact. So I think I told you the story when I was 16 years old and I turned the wheel and it didn't go. I had no friction. Well, that same story, I actually experienced a airbag, and it's actually like not like you see all those commercials and it flows out and it's this puffy little thing and you're like, oh, that looks comfy. No, it was like a punch in the face. It came out so big and so fast I couldn't even get over it. I like bruised my nose from it. It was so hard. So they're not like these little fluffy marshmallow pillow things. They're actually pretty hard. But despite feeling that, I was certainly lucky and fortunate that I wasn't injured any more than that. And if I hit the dashboard, it would be a different story. So what I'm going to do is calculate the force felt during an airbag versus the force felt during hitting the dashboard. And this is, taking an average mass of person, which is 70 kilograms, traveling at highway speed. So 35 miles per hour is about 70 miles per hour. So you're going fast. This is a fast speed here. So let me go ahead and annotate this. Oopsie. I want that one. And do this. Okay, so I'm going to use the impulse momentum theorem. It's just a really big word for this equation, just like the work energy theorem. Here we go. Now, notice I took out delta t. Delta means the change in time, which I'm just going to simplify as t. Normally, if you have a time duration that's not 0, you would just find the interval of time. So in this case, I'm just going to use the interval of times, which are given up here. So I'm going to do both cases. So I'm going to go ahead and just scroll down so I have some space. So case with the airbag, and then case of dashboard. So according to the question, the mass of the person, and you can go back, I just happen to memorize some of these values, is 70 kilograms. Now, if I come into a, if I collide with something, my final velocity will be 0. Well, that's not always true, but in this case, we're using 0. Minus the initial velocity, which was 35 meters per second. We're calculating force, so I'm going to leave that as t. And I believe the time the airbag, you feel the airbag, it's still less than a second, is 0.75 seconds when we do this. So I'm going to go ahead and do this calculation. So I did this side first. So I get negative 2.450. This will be kilograms meters per second is equal to force times 0.75 seconds. I divide both sides by that. Oops, that's okay. I know what I'm doing. Is negative 3266.67 if I round it, is equal to the force. So you experience a lot of force here. And notice the negative just means the force is opposite your motion. So naturally for something to stop, it's going to go in the other direction. So that's what that negative means. So I'm just going to do a side calculation here. This is not necessary to know, but I'm going to find how many G's this is. So 70 times 9.81, 686 newtons. So that's how many G's this person will feel. So if I take that number, I'm just doing this is totally side calculation. Divided by the G's. The G force is what I'm finding here, because I'm curious. 66.67. Wow. 4.1 0.76 Gs. I'll tell you this, you know that feeling when you get on the roller coaster when you get pushed down? This is way higher. That's about 2 Gs you feel on a roller coaster. Some roller coasters do 3 Gs. This is about almost 5 Gs. This is like astronaut business here. So when you get into a car accident, you're feeling 5 Gs with the airbag. Crazy, right? Crazy. So we're going to do the same calculation, but basically I'm just changing this time. So the setup happens to be the same. So the mass is still 70. The final speed is 0. The initial speed is 35. Same scenario. Looking for force, but now the time is, I think, 0.26 seconds. So I'm going to be much quicker with this calculation and just go right to the force. So 2450. 0.026. Negative 94,230.77 crazy high newtons. How many G's is that, you ask? I don't know, 137.36 G's. Yeah, that's pretty much lethal. I mean, I don't have a case to compare that with because that's so ridiculously high. I think astronauts can go up to almost 10 Gs, I'll tell you that. So there you go. This is, I mean, that's just crazy. So look at how much of a difference this is. I mean, this is still really high in force value, but what a difference then it is to hit your dashboard. So we are very fortunate to have those dashboards to help us save our lives as such. So that's using the impulse momentum theorem. It's really helpful for understanding, the impact of the times. And notice that if you increase the time, assuming the change of velocity is the same, if you change the velocity is the same, then if you increase the contact time, you definitely reduce the force, like rolling with the punches and etc. like that. And you can see physically these numbers of doing that. These are just some more calculations. Sure, I'll set it up for you. I'll do it. I'll do the calculation for you. Just another way you can see kind of the same thing. So we're going to use the impulse momentum theorem again. And when I do, I have the mass of the car. Oops. 240 kilograms. So it slows down from 20 to 5. So 5 is the final and 20 is the initial. It gives us the force. It's positive because it's going east. And we're looking for time. So that's the setup of this question, is looking for time. All right, let's go ahead and simplify this. So I'm going to do 5 minus 20, which is negative 15 times 2240, negative 33600 kilograms meters per second is equal to this. Okay, just checking that, times t. So now I'm going to divide that by 8410. And if you notice, I did make a mistake. I'm going to show you my mistake so you can hopefully learn from it. So my answer became negative 3.99 seconds equals time. So hopefully this is a red flag. Because time should not ever be negative. And I was right. I know my mistake. So my mistake was this. I'll show you. When I was looking at this, I see that it does say east. And I was like, oh yeah, east. That makes sense. So I'm going to call this positive because that's east, and I did that correctly. What I did wrong is that this car is traveling west, which means these numbers, are negative. So -5 minus -20 is in fact +15. Boy. Which makes that number positive, which then makes that number positive. Okay, I fixed it. See, gotta read the questions. But it's okay. Sometimes you miss those small details. It happens all the time, and it's okay. But just be aware of things like direction. It's like I did, okay? So anyway, time is basically 4 seconds, if you notice, if I just round it out anyway. So it takes 4 seconds for the car to decelerate when it feels that force. How far does the car traveling during deceleration? This is a bonus question because this is more of a kinematic equation instead of one of the equations that we did. So let's see. We have a final velocity. I'm going to write down everything that we have. Negative. Oh, I messed that up. Live on camera, I messed it up. Okay. Life goes on. 4 seconds. I have final velocity, initial velocity, time. I do have force, but for kinematics, it's not helpful. So the kinematic that would be helpful is this one. Final, initial, time, just like I have. So we're going to go ahead and do that. So 1/2 -5 plus, meters per second, -20 meters per second. This is going to come out negative. Oh, that's fine. Okay. Oh my gosh. What's happening? I'm going crazy. All this stuff is going. You're watching it happen. It's unfolding live on camera. Oh my goodness. So I'm calculating this 0.5 plus -20 times 4. I get -50, which scared me for a brief moment. But it's okay, everybody. It's okay. Because -50 just means we went 50 meters west, which makes total sense because we were going west to begin with. So everything works out. See? Gotta trust physics. It works. Okay. There you go. I'll post a separate demonstration of me throwing an egg into a sheet. This is a very good crowd pleaser, but this requires a little more help. I can't do this by myself. Usually I have class volunteers for this, so I'll post this as a separate demonstration anyway, and I'll show you all about this. So yeah, that is impulse and momentum. So just a little summary on this whole lesson here. A force causes a change in momentum, and it's very powerful because not only do you include inertia, or the mass of the object, now you think about the object's motion. So you could have, a large momentum with a very small object. For example, like a bullet moves really fast. So even though it's like teeny tiny, it's got a very fast speed. So that actually has a lot of momentum. Or you have something that's slow, massive, right? Like a cruise ship, coming into the dock, it moves pretty slow. But that thing, you won't change its momentum. Or you can have both, like the sun, who is not only super massive, but is actually whirling around our galaxy at a pretty fast speed. So that's an incredibly large momentum. So that will keep its motion, which is good because we want it to do that. So in order to change an object's motion, you need an impulse, which is basically a force that's applied over time. Impulse is the change of momentum. They're in fact related with the impulse momentum theorem, and you can combine the two equations to solve questions using it. The area under a force versus time curve is impulse. So basically you're solving basically geometric shapes. You're finding the area of a triangle or of a a rectangle, or if it's a weird shape, break it down into triangles and rectangles and then add them up. But they shouldn't be super complicated when you do it. And as long as the change of velocity is the same, you'll find that if you increase the contact time, you'll reduce the force. This is why if you, I don't know, get stir crazy and throw your mattresses on the ground and you run and jump on top of your mattress, that it cradles your fall because it increases the contact time, unlike the unforgiving floor, which has less contact time like that. So those are the main ideas of impulse, momentum, and the impulse momentum theorem. Let me know if you have any questions regarding the content, and hopefully the homework doesn't, hope the homework as always is straightforward. Challenge you just a little bit, like a little challenge. But hopefully everything else, goes smoothly. If you don't understand everything, just give me a holler and I'll be happy to go through it with you. Have a good one.